Alright, welcome ladies and gentlemen. This is video number 2 in our thermodynamics unit. In this video I'm going to be talking, now that we know what the three thermodynamic quantities are, we understand what their signs are saying, how the signs actually unite the big three together and how they can sort of be used in common. Now, the way that they are used together is through this equation. Delta G naught equals delta H naught minus T delta S naught. This right here, this is the rock star. This is the big formula. This is really the big one. And it unites the three together, uniting the three thermodynamic quantities. This is the huge one that we're going to want to be referencing like most of the time. This is kind of like PV equals nRT in the gases unit. This is the big formula. Comment though, before we talk about the signs on our three quantities, units on delta G naught, kilojoules per mole reaction. Units on delta H naught, kilojoules per mole reaction. T, I'll come back to in a sec. Units on delta S naught are joules per mole Kelvin. So comment about that right there. We've got kilojoules, and joules. Super common that we typically want to convert our delta S value from joules to kilojoules in order to match it up with delta G and delta H. Now looking at this, what unit does T have to be? Well, again, look at the units. If these are the units on delta G, delta H, and delta S, where's the one that has temperature? Delta S, it's in entropy. And notice it's in Kelvin. So temperature must be in Kelvin here. And this is just like, this is for the exact same reason that temperature has to be in Kelvin when we're talking about gases. Temperature has to be in Kelvin when we're talking about gases because we can't have negative pressure. We can't have negative moles, right? We have these absolute amounts. And it's a similar idea here. But not quite exactly the same. It's not that we can't have negatives, but what it is saying is that now the negatives mean something. The negative for delta G means something. Negative for delta H means something. The negative for temperature doesn't mean diddly squat. It just means that the temperature is low. That's all it means. It doesn't mean anything other than, oh, it's got a really small temperature. So the negative versus positive has a huge meaning for all these other quantities. So we need a temperature that doesn't have that same temperature scale, that doesn't have that same sort of implication, because the negative in Celsius doesn't mean anything. So we need this like absolute temperature scale when we're using this, because the positive versus negative means very distinct things for everything else. It doesn't mean anything for temperature. So we're going to take away that question of negative versus positive for temperature. So temperature is always positive when we're talking about this, which means that when we talk about signs, we're not including temperature in that conversation because the temperature sign isn't going to be changing. But signs on delta G, delta H, and delta S can change for everything else. So in order to talk about the importance of signs, we want to consider all possible combinations of signs for entropy and enthalpy in the terms of this formula, delta G equals delta H minus T delta S. Before I get into that, though, I will add that delta H and delta S, they're assumed to be what's called temperature independent, which means that their value and their sign doesn't change for a reaction depending on the temperature they're at. So if you have a temperature that's running at, let's say, 298 Kelvin, and delta H is negative 100 kilojoules per mole reaction, then if you change the temperature to 400 Kelvin, then it's still going to be negative 100 kilojoules per mole reaction. So your delta H and your delta S values, they are not changing as temperature is changing. So they're fixed values. They are often assumed to be, that's what it means when it says temperature independent. So what possible signs can we have here? Well, we can have a process that's endothermic and whose entropy is increasing. This is a process whose delta H value, if it's endothermic, it's positive, but the delta S value is negative. Entropy is decreasing. So what does that mean in terms of this formula, delta G equals delta H minus T delta S? Think about signs, and this is what I'm going to do. I'm going to sort of plug in, but I'm only going to plug in with signs. So if delta H is positive, and then I'm subtracting from that, I'm not thinking about temperature because it's always going to be positive. I'm subtracting from that a negative. Well, what do I get from that? Well, if you have a positive and then you subtract from it a negative, there's only one sign that you can get. Delta G is going to be positive. More than that, delta G is going to be positive at all temperatures. So this process, one that is endothermic, whose entropy goes down, is non-spontaneous at all temperatures. And then the next one, what if you have something that's exothermic, but entropy goes up? So exothermic, that's a delta H that's negative, and entropy increases. That's a delta S that's positive. Same idea. We have this formula, delta G equals delta H minus T delta S. Well, now I have a negative value, and I'm subtracting from that the temperature. It's always positive, so I'm not plugging in anything for T. I'm subtracting from that a positive value. A negative minus a positive, well, we can math. We know what this is going to be. This is going to be a negative value, but it's going to be negative at all temperatures. There is not a single temperature that you can plug in here that would give you a positive number. It's always going to be negative. So this process right here, this is spontaneous always, spontaneous at all temperatures, meaning delta G is negative always. But if we have an endothermic process, so delta G is positive, where entropy increases, where delta S is also positive, now we have a situation where we have a positive value minus a positive value. We cannot predict a sign, right? We can have two possible answers. We can have a negative or a positive value here. So now it comes down to a question of temperature. If you have a positive minus a positive, when do you get a positive value from that? Well, you get a positive value from a positive minus a positive if your second bit right here, if that second bit right there is small. Well, what could make that second bit small? Well, it's not going to be the delta S value because that's locked in. That's what I mean when I say that delta H and delta S are temperature independent, meaning delta S is not what's making that second bit small because delta S is a fixed value. What could make that second bit small? Your temperature. So if that second bit is small, meaning if temperature is low, then we can get this positive value for delta G when you have a positive minus a positive. But when do you get a negative number? Well, you get a negative number if that second bit, this bit right here, is actually very large. If it's larger than the first bit, than the delta H, then you'll have a negative number. So when is it negative? If temperature is high. Because the temperature is what is controlling the magnitude of the second portion of this subtraction. So this endothermic, but entropy increases. This is spontaneous at high temperatures, but non-spontaneous at low temperatures. And then the final one, an exothermic process, delta H is negative, where entropy decreases, so delta S is negative. Now we have a negative minus a negative. Well, what do you get if you have a negative minus a negative? Again, we have two possibilities. It can be either positive or negative. The positive portion of this is really this, right? Math says if you subtract a negative, that's basically you're adding it. I'm sure there's some fancy rule that has a name that I'm not remembering right now, but you subtract a negative, you're basically adding it. So when do you get a positive value? You get a positive value if this second portion, this thing right here, is larger in magnitude than the first portion. And again, what controls that? Well, not delta S and not delta H, because they're fixed values, but the only thing that is allowed to change, which is temperature. So this thing is going to be positive if the temperature is high, meaning if it is larger than the first bit, but it's going to be negative if the temperature is low, meaning if that second positive bit is smaller than the first negative, then we're going to have an overall negative number. So if temp is low. So this exothermic where entropy decreases, this is spontaneous at low temperatures, but non-spontaneous at high temperatures. Now, the next slide simply summarizes this into a little chart. But what I really want to say, first of all, this is hugely important. We absolutely have to understand this. I do not want you memorizing this, because if you memorize this, you will not understand what this is saying, and you will forget it, and you will get it wrong. What I do want you to be able to do is to reason your way through a problem. So, for example, right here, consider the reaction A goes to B that has a delta H of positive 137 kilojoules per mole and delta S of positive 120 kilojoules per mole. How will spontaneity change as their temperature increases, and justify? If you memorize this, you will get this wrong. But if you reason your way through, you'll get it right every time. So how do we want to justify? Well, we want to say, we know that we're going to use this formula, and sorry, not equals, but a minus, and you want to actually write it out as part of your explanation. A delta G equals delta H minus T delta S. We know that we can bullet point, right? We know that we don't need to write incomplete sentences. So that's exactly what I'm going to do in explaining this problem. I'm going to start by referencing this formula. I'm going to include it, and then I'm going to plug in our signs. Our delta H is positive, our delta S is also positive. So I'm going to say, okay, positive minus a positive. Then I'm going to think. And I'm going to actually legitimately write it out just like that as part of my explanation. So, okay, a positive minus a positive is asking what happens as temperature increases. So as temperature increases, we're going to be increasing the magnitude of this portion, right, this T delta S portion. So as temperature increases, T delta S will eventually become larger than delta H, right? The magnitude of this second bit will become larger than the first bit. And we have a positive minus a positive. So the reaction, for that reason then, as the temperature increases, as the second bit becomes increasingly large, then it will become larger than the first bit, and the second bit will now be the negative thing. So the reaction becomes more thermodynamically favorable, which just takes me forever to write out. Thermodynamically favorable, meaning delta G is negative as the temperature goes up. Which, there we go, we've answered the question, how will the spontaneity change? So as the temperature is increasing, the delta G is going to become increasingly negative. It's going to become more spontaneous at these higher temperatures. And there you go, you've answered the question. Notice though that I didn't memorize. It's just like, okay, let's show the formula, let's sort of plug in signs, and then let's just use it to reason our way through and answer the problem.